What if we have a mixture of gases? We're going to go back to talking about ideal gas conditions. According to kinetic molecular theory, the particles are so small their size doesn't matter. They're moving fast enough and there's enough empty space between them that they don't interact with each other. The components of a gas mixture act like they are the only gas in the sample, in that container. So the pressure of any individual component in that gas mixture is going to be the same as if there wasn't another gas in there. I'm trying to think of a politically correct analogy. I'm not coming up with one. Not one that's politically correct, so we'll go with politically incorrect. Cowboys and Indians. So no offense is intended. So Wyoming, it's a western state. Lots of space. Lots and lots of space. And so maybe there are some Indians living in the upper northwest corner of Wyoming. And some cowboys move in. And there's enough space there that they don't actually even really notice each other, right? Because there's so much space, they just act like they are the only people there. And that's what happens when you have sparsely populated areas. People don't really know about their neighbors. That's not going to happen in a city where if people who are offensive to you move in right next door to your townhouse, you're going to have some issues with each other, right? So the gases, because there's these huge spaces between them, they act like it's the only gas there. So each of those gases in the mixture is exerting a pressure, just like it was the only gas there. And we call those pressures partial pressures. And if we take the partial pressures and add them up, we get the total pressure. The partial pressure of any component is equal to that component's fractional composition times the total pressure. I think I've got an equation. No. Yeah, it's coming. Okay, we'll just be patient. So if we think about the air, air contains about 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and then the rest of it is made up of other gases in very tiny amounts. So nitrogen exerts a certain pressure. The air is exerting a pressure. We don't notice it because we're used to it, but it's always exerting a pressure. 78% of the gas particles are nitrogen molecules. The nitrogen molecules exert 78% of the total pressure. The oxygen is 21% of the mixture. It exerts 21% of the total pressure. Because the crazy thing about gases is what the particle is doesn't matter. It just matters how many particles. And the pressure of the oxygen is independent of the presence of the other gases. So here's an illustration. A mixture of helium and neon. So there's 20% neon and 80% helium. There's 10 particles in there. There's 2 red ones and 8 blue ones. If the total pressure of this mixture is 1 atmosphere, then 8/10 of the pressure is from the helium and 2/10 is from the neon. It's proportional. So what we're talking about with a fractional composition is we take the percent composition and divide by 100. So in this example, 80% helium. 80% is 80 per 100, which equals 0.8. That's the fractional composition. And you multiply that by the total pressure of 1 atmosphere, and you get the partial pressure of helium being 0.80 atmospheres. And the rest of the pressure is made up by the neon. 20%, 0.2 times 1. I don't know what my computer is doing. So let's do an example. Gas mixture contains 64% methane, 36% ethane, if the total pressure is 1.44 atmospheres. What are the partial pressures of each component? So we've got methane and ethane. I'll try that again so it's not off the screen. Methane. And, you know, these could just as well be named Tommy and Michael or something. We don't need to know what they are to do the problem. Methane is 64%. How do we change that percent into fractional composition? Just divide by 100. So its fractional composition is 0.64. And for the ethane, 36%, divide by 100, we get 0.36, the fractional composition. So to find the partial pressure, we're going to take the fractional composition, 0.64, times the total pressure. If it was even, if it was half methane and half ethane, the pressure of each would be the same, and they would each contribute half the pressure. So 0.64 times 1.44. 0.92 atmospheres for the ethane, the methane. And for the ethane, it's 0.36 times 1.44 atmospheres. 0.36 times 1.44, or you could just take the other one, subtract it from 1. Oh, I did something wrong. I came up with, no I didn't. Never mind. Oh, I'm just blithering. 0.52 atmospheres. So this one exerts 0.52 atmospheres, this one exerts 0.92 atmospheres, and those add up to 1.44 atmospheres. Any questions? You could do problems like this with boxes of fruit, too. If you had a big box of fruit and 36% of it was apples and 64% of it was oranges, and the thing weighed 100 pounds. Well, what's the mass of the apples? What's the mass of the oranges? You do the same thing. And that brings us to another gas law. It's kind of a different sort of gas law. It's called Dalton's gas law. Dalton's law of partial pressures. So this says that the total pressure of a mixture of gases is the pressure of each individual gas added together. So if we look at air at 1 atmosphere, we were looking at the fractional composition of air, and using those equations, we would find that the pressure of nitrogen is 0.78 atmospheres. The pressure of oxygen is 0.21 atmospheres. The pressure of argon is 0.01 atmospheres, and the rest of it's so small it doesn't really matter. We add these together, and they add up to 1 atmosphere. A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 745 torr, and the water vapor has a partial pressure of 24 torr. What's the partial pressure of the hydrogen gas? So the total pressure equals the pressure of the hydrogen plus the pressure of the water vapor. That's Dalton's law. The total pressure equals the pressure of each individual gas. What are we trying to find? The partial pressure of the hydrogen gas, right? So this guy. How do I rearrange that equation and get pH2 by itself? Subtract. So pH2O is over here, but these are added. I don't want to divide. I want to do the opposite. I'm going to subtract. So I'm going to subtract PH2O from this side. And then I end up with, oops, PH2 plus 0, right? If I subtract from one side, I have to subtract from the other side. And over here, I end up with the total pressure minus the pressure of water. And those are equal. So the pressure of the hydrogen gas equals the total pressure, which is 745 torr, minus the pressure of the water, which is 24 torr, that gives me 721 torr. Any questions? Sometimes these seem too simple compared to all those more involved multiplying, dividing all over the place.
Yeah, I thought it's no further unit conversion is required unless it's asked.
Right. There are sometimes unit issues. Here they gave us the total pressure in torr and the partial pressure of 1 in torr. Sometimes they'll give you a problem where they'll give you 1 in atmospheres and 1 in PSI and 1 in millimeters of mercury and 1 in pascals, and then ask you for the other thing in something else. And that just makes you convert a whole bunch of units. But the units for these pressures have to be the same, because otherwise it's like adding apples and oranges. You can't do it. The units have to be the same. Any other questions? This idea of partial pressure is important in deep sea diving or scuba diving. Our lungs work best when the oxygen partial pressure is 0.21 atmospheres. And here's a little graph. This is normal air at the surface, has 0.21 mole fraction of oxygen. As you increase the amount of oxygen, you can get to actually an oxygen toxicity. So this would be 1.6 would be the maximum of oxygen, and above that oxygen toxicity, you can get you can be killed with too much oxygen. But not enough oxygen is bad also. It's like so many things. There's this middle ground, moderation, right? Too much water kills you, not enough water kills you. Too much oxygen kills you, not enough oxygen kills you. So when you go to higher elevations, the total pressure decreases, and so does the partial pressure of oxygen. And so then that's why, you go up to the mountains and you get winded a lot easier, because your body is just not used to taking in those lesser quantities of oxygen. What happens at the surface, when you go deep sea diving and you go to deeper and deeper pressures, the pressure of the gas that you're breathing, the air in the tank, has to be greater so that you're able to, inhale, expand your lungs, because all this water is exerting pressure on you, and if the pressure of the gas that you're breathing isn't great enough, you won't be able to expand your lungs and you're not able to breathe. When the total pressure increases, then the pressure of oxygen increases as well. So at 30 meters, the total pressure is 4 atmospheres. Now the pressure of oxygen is 0.84 atmospheres, not 0.21, like our bodies prefer. And when you get to higher and higher oxygen concentrations, you get into oxygen toxicity. You've got twitching and tunnel vision and convulsions. And you can imagine if you're 30, 40 meters below the water, These are really not good things to have happening, and you're not going to have clear judgment and maybe recognize what's going on. So what they do is they add more nitrogen to the pressurized air, so that at 4 atmospheres of pressure, you're getting still about 0.21 atmospheres of oxygen. And so that's really good. But then you can also get too much nitrogen. That's referred to as rapture of the deep. Apparently it feels like being a little bit drunk. And so that's not a good thing either. And so for deep sea divers that go very deep, they actually use a special mixture called Heliox, which is a mixture of helium and oxygen, because helium does not do that to us, although it does make your voice really, really squeaky. But nobody can hear you talking down there. So anyway, this whole idea of partial pressures is very applicable to some aspects of life. And it also has an impact in terms of someone in the hospital needing oxygen to supplement and help them to breathe. The ratio of oxygen to other gases is very important. So let's do an example. A diver breathing Heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres. What does the total pressure need to be? So we want the partial pressure of oxygen to equal 0.21 atmospheres. The partial pressure of oxygen was the mole fraction, which they never really give us. It's actually the Greek letter chi. That stands for mole fraction. I'll write that down here, mole fraction. Times the total pressure. Do we know what the mole fraction of oxygen is? Do they give it to us? Kind of. What does 5% mean? The mole fraction of oxygen is that 5.0% divided by 100. So the mole fraction is 0.0050. That's the mole fraction. I want to find the total pressure. So I need to take this equation and rearrange it, which means I also need to get rid of this because it's in my way. It's not how I get rid of it. That's better. So I'm going to divide by mole fraction of oxygen on both sides. Mole fractions cancel out. The total pressure equals the partial pressure of oxygen divided by the mole fraction of oxygen. So that is 0.21 atmospheres divided by 0.0050. And that equals 42. Seems really high. Oh. Yeah, that's because I did this in my head and I put an extra 0 in there. It's 0.05. It's 0.05, so it's actually 4.2. Well, let's just really fix that. 4.2 atmospheres. So if you have 5% Heliox, then you need to have a 4.2 atmosphere total pressure to get your 0.21 atmospheres of oxygen. There's a reason they make you take all these classes before you can go scuba diving. It's because it's a lot more complicated than it looks. There's some things you have to know to keep yourself alive. Any questions? One way to collect gas that's generated in an experiment is to collect it over water. It's actually be more accurate to say collecting it through water. So here we have a test tube. Oh, that's not what I meant to do. Here we have a test tube. We've got zinc and hydrochloric acid. And when those react, they're going to generate hydrogen gas. And we can collect the hydrogen gas by connecting this container with a tube coming underneath an inverted beaker of water. This beaker started out completely full of water. And as the hydrogen comes in, it displaces the water. It bubbles through the water and it displaces it, and then we end up with hydrogen gas up here. But we also have water vapor because the water evaporates. So we have a gas mixture. We have water vapor and we have hydrogen. If we want to know how many moles of hydrogen we made, we can measure the volume, the temperature, the pressure, and calculate the total number of moles of gas. But we have to do something about the water vapor because it can be significant. So in here we have the pressure of the water and the pressure of the hydrogen. For water vapor, we have a special name for its partial pressure. It's called the vapor pressure of water. And the vapor pressure of water depends only on the temperature. And so we can actually just look up a table. Other people have measured this for us. And here's an example of a table. At 10 degrees, the vapor pressure of water is 9.2. At 40 degrees, it's 55.3, etc. So hydrogen gas was collected over water. Anytime you see over water, that means there's water vapor in there. You're going to have to use Dalton's law of partial pressures to correct the pressure. So the total pressure is 758 millimeters of mercury. The temperature is 25. What's the partial pressure of the hydrogen gas? Well, the total pressure is going to equal the pressure of the hydrogen plus the pressure of the water vapor. We want the pressure of the hydrogen gas. So we subtract the pressure of the water from both sides. I'm not going to go through that again. And we get this. The total pressure minus the pressure of the water. Well, the total pressure was given to us, 758 millimeters of mercury. The pressure of water, we look up in this table. The vapor pressure of water, the temperature is 25 degrees, so here's 25, and there's the vapor pressure, the partial pressure of water. It's 23.8. So 758 minus 23.8, 734 is the pressure due to the hydrogen. Any questions?